This computer, yes. Okay, now we're recording for real. Okay, so this is brute force week, right? Brute force, you hit something with a hammer until it gives up, basically. There's no finesse, there's no style. You just take the long way around, okay? It turns out to almost always be the worst way to do things, but the saving grace is that computers do repetition fast, and computers don't complain or take lunch breaks or take coffee breaks, any of that stuff. So, I mean, there are worse things than just letting the computer grind away at the problems. Okay, so yeah, it's a mixed bag. It's often the case with algorithms that you have to try to figure out, is it worth the extra effort to make things more efficient? If it's not going to be used much, or it's not going to be used in any kind of a high pressure situation with a bunch of data, then you don't sweat it. Okay. So we talk about some different kinds of problems there. So I do want to say about the problem sets in general. Okay. So as far as grading, as far as what I'm trying to get, a lot of the word problems, I guess you would call them, are subjective in that there's a best answer. I don't know that you're going to find it. I don't know that I'm going to find it until I look it up. Okay. The coin weighing problem is an example of that. I was doing it in 3 ways. The book found a way to do it in 2 ways for their solutions. And they're ingenious solutions, but that's almost a creative endeavor. So certainly on an exam, I would not expect you to be able to pull an elegant, beautiful algorithm, out of your head. Just like I wouldn't expect you in a poetry class, write a poetry poem right now. So that's not really what we're looking at. And as far as the homework goes, I'm looking, are you making reasonable effort, reasonable solutions to the problems rather than getting them exactly right? Okay. The feedback has been an issue in that they're all PDFs, which is good, but I'm not able to write them up or mark them up. So I'm trying to figure that out. Normally I would print them out, but then how am I going to get them to you? But I'll figure that out. But I know some of you are missing a level of abstraction, okay, that's important in this one. Like there was somebody in one of on the problems from last week that I was looking at on how many multiplications will there be? And they're like, that's indefinite. You don't know. Well, if you know that n is a number of elements, or n is the number of the order of the matrices, then n squared is a number of elements. So you can talk in terms of n. You make that abstraction. So those questions are never asking you how many, like a number like 5, right? It's all in terms of variables. And we're not used to normally, I mean, depending on what you do as far as your teaching goes, but most people are not normally used to dealing in those abstractions, okay? So a lot of those, the 3 jugs problem this week, it's just, I think those are fun to work with. And if you can work through it and enjoy working through it, then great. And I'll post the solution next week. But if you don't get it, not the end of the world. Okay. It's the process that's important. Okay. But I do think, and thinking about the portfolios that you guys have to do, a lot of those word problems can be turned into physical things, right? You could physically do these things. And, I think that would make some sense. So the portfolio, you're doing lesson plans, is that right? Is that the idea, that you have to do a lesson that you could do with your students? Is that correct?
It can be lesson plans or worksheets or activities, or
okay.
They're called artifacts.
Gotcha. That makes sense. Well, I think I'm going to put an assignment out there with next week's stuff, probably on divide and conquer. So you can be thinking about it of an activity you could do with whatever age group that you do that shows the difference between a brute force solution and a divide and conquer solution. And I think that even with the youngest kids, I think there's some manipulatable things that you can do with that. So rather than doing everything one at a time, can you split them into groups in some way? So I'm going to leave it to your creativity to work through a solution on that. So hopefully that will be something that you can put into your portfolios. I often forget to worry about the portfolios, and that's unfortunate, but I don't normally teach teachers. So, it's new to everybody, I guess. But
I think they should throw cream pies at each other, though.
Well, probably not. But maybe,
that could be bad.
Maybe like fake cream pies. I know the problem that I didn't give that you guys really should look at, because it boggles my mind every time. It's the frying hamburgers problem. I don't know if you looked at that one or not. It's if you have 2 hamburgers to fry, what's the most efficient way to do it? No, sorry, 3 hamburgers. It's a 3 hamburger problem. And you would think that you put 2 hamburgers on, flip them over 2 more, then do that 2 more times, right? So a total of 4 cook times. It turns out there's a solution with only 3. And that just is counterintuitive. And I think that would be a visual enough thing. So if you're at a loss at what I'm talking about for an example for your class, look up that 3 hamburger problem, that there's a faster way than just frying your 2 hamburgers and then frying the 3rd hamburger. So yeah, it's very interesting. So algorithms can be very non-intuitive sometimes, that there are solutions that you don't think that there could be. And that's kind of like a life skill that you could teach your students, no matter the level, to look beyond just the, hit it with a hammer till it dies. There may be some finesse possible. So I think that's the value. This seems to me a more valuable class than some of the others that you've taken as far as practical kinds of skills. If you're curious, there's a really good book. This book, I checked it out from the library as an audiobook, and I liked it so much I bought a copy. It's called Algorithms to Live By, I think. And it's applying algorithmic thinking to crazy things, like how many people do you need to interview before you feel you've got a good pool or whatever. And there are algorithms for all kinds of things you wouldn't imagine. And it's fascinating to see how that works. So it's a powerful tool. Okay, I've rambled enough. So what do you guys want to talk about? I do have some questions. Somebody who was not sure if they're going to be here. Now, I don't remember who it was. I don't know if they're here or not, but I do have some questions if no one else has any. So what are your questions?
Well, I wanted to ask about the number 7 and 3.1, because I saw the coins and I thought, oh, another coin problem.
Yes.
But it seems, I mean, like, I don't know. I feel like it's really easy to overthink, especially after last week's coin problem.
Yes.
Because that one was about to kill me. We're just trying to like do the code and make sure you get all the different cases and whatever. But
this one, you have a real scale. You have a precision scale. So this one's a little different, right?
That's what I'm thinking. Like, so, I mean, that's what it's saying, right? Like you can just weigh them and it will tell you how much it weighs.
Yes.
Okay. So so when it says devise a brute force algorithm, I mean, we're just basically saying don't overthink that. Just write down what you're going to do.
It's brute force, right?
Because it says devise a brute force algorithm. So it's like you're supposed to come up with something.
And they're in stacks, right? They're
like
not
you
individual.
just weigh them until you get the one that weighs more.
You hit it with a hammer until it dies, right? That's what you do. You weigh 2. Then you weigh 2 more.
So you said they're not individual. You weigh them as stacks.
Yep.
And it's correct. A stack that's fake. So that's the thing. Like
the whole stack is fake, yes.
Yeah.
And it weighs more, you know that. Right?
Yeah.
So there's no fancy way.
The only way that it'll weigh the same thing is if it's like 10 of them, so 10 times 11, I guess, is like where you're going to have a little different math, because then
this isn't the scale thing. Yeah, you'll weigh each stack. If the stack weighs 10 times n, then you know that
it's real.
Is okay. If it weighs 11 times n, you know that's not okay. So you just start weighing stacks until you get one that weighs 11 n. If it weighs 11 times n, then you know you found your fakes. Okay.
So we could use an algorithm like on page 47 with the outputs, inputs.
Yeah, it's going to look like that, right?
With a while if.
Yes.
So, do you want pseudocode for that?
Yes, sure.
Oh, okay.
When you see the word algorithm, think pseudocode. Okay. Because that's a weird format. So the more you can practice, the better off you are. Okay. Part B of that requires a tricky answer. But I'll tell you, there's a hint. You can get by with one weighing.
Well, you just kind of said it before.
Stack. but there's a tricky way to do it. I didn't say how. There's a tricky way to do it. But you know, it's 1, right? I will tell you it's
I'm
1.
glad you said look at B for some reason. I thought it was just 7A. I don't know why.
I don't think I said 7A. Maybe I did. If
No.
not, do B anyway. B's fun. It's fun to figure out. You may or may not get it, but there's a pattern to solving a lot of these, logic problems that you learn after a while. But so did that help somewhat, Kim? I think Kim's asked that.
Yeah, I wasn't thinking in terms of pseudocode. So I was just like, well, don't you just say you just weigh each one until you find the one?
Right, but but the next step then is to learn how to put that into an algorithm, right?
Okay.
So that's going to be the point. So
Okay.
while the weight is not equal to 11n, then weigh a stack and then keep going from there until you get that 11n. Then you know you found stack.
Hey, David, I am totally missing the complexity of B because I mean, you would only have to, I mean, at minimum, you would weigh, I mean, in the best case scenario, you would only have to weigh 1 and that would be it. So I don't understand.
Oh, that's
else
weird.
is
And
behind
the way the book answers it is different from that. Okay, what is the minimum number of weighings? Yeah, right. Not in one case, but no matter where the fake stack is. That's not worded well. But what they're saying is if you have 10 stacks with 1 weighing, you can tell which of those 10. So not getting lucky. So this isn't like a best case scenario. This is like how in 1 weighing can you figure out of n stacks of coin which one's right, and you don't have to get lucky and get that the first time.
Okay.
So it's a different problem. Okay. And if you don't get it, don't lose any sleep over it. Well, lose a little sleep. Don't lose a lot of sleep. It's a fine line here. I don't want you to just not even try, but I don't want you becoming, psychotic or more psychotic maybe than you already are. So.
Yeah, because right now I'm not seeing that. Because I'm like, you got to weigh them all. Or
yes.
And 2. I don't know.
But once you know the answer, you'll be like, that's really cool. Or at least that's really cool. And you put it away like, okay, maybe I can use that again somewhere.
Okay, so we'll know the answer Monday.
Yes, or so. More like Tuesday. I don't have other classes Tuesday.
Logic is not my strong suit. And so I'm really worried about all these logic problems.
But the key to think about is that all the coins weigh the same except 1 stack. So they all weigh 10, except 1 stack where they all weigh 11. And I'll say that part B's answer depends on them all weighing 11. If there's only 1 bad coin, it wouldn't work. You would need more. You would need the 2 like we did last week. Okay, but you've got a whole stack of them.
So
are
you still using that scale to where you would be measuring them against each other?
No. This is a precision scale that gives you a number.
Okay.
You'll put a stack on. If there are 10 of them, it'll say 100 grams or whatever grams. Yeah. So then that's a real one, right? If it says 11 or 110 grams, then that's a fake one.
Okay.
Okay. Other questions? I am recording. Yes, I'm paranoid now about recording.
Well, I was going to ask you about brute force string matching, but since you have redone the video, I'll just wait and watch it.
Yeah, it's not bad. I think what throws people off sometimes, I mean, you're just going to start matching, but if you're trying to match a pattern of 5 characters long and you've got 100 characters, when you get to the 95th character, you don't have to go any further, right? Because you can't fit 5 characters into less than 5 left. So you don't go all the way to the end, okay? That's really
So the pattern for Gandhi is 6. So if we're comparing, do we use the space? I'll just watch the video.
Yeah, you
then
can.
Then you'll be repeating yourself.
Usually, it's okay. Usually you use the space. I mean, it doesn't matter. You can decide. It's not going to be the space in this case. So either way is going to be okay. But all you compare is the first character, right? So you compare the G in Gandhi against the first character. And if that's not it, you move to the second character. But if it is a G, then you look at the second character, and you kind of go from there. And I do an example in the video of that, but that's the idea. And I think the other question it asks is about a worst case scenario. And the worst case scenario is going to be every time it gets really close. Like the worst case scenario for Gandhi would be the first 5 letters repeated over and over again, right? That would take the most number of reworkings. It would every way. I'm almost there. I'm going to do all 5 of these. Oh no, now I go to position 2 and do them again. That's the worst case scenario. Okay.
I think I got confused because looking at page 106 with that picture doesn't make sense to me. Like It's like the N matches and the O matches, but the T doesn't.
Yes.
And then it's like, but they did.
Then you stop.
Right. And then the N, so they're looking for the word not. Is that what they're looking for?
I'm guessing. It should say somewhere, but I don't see what.
Okay, so I see. So then they find it.
Yes,
so
it's not.
Right. So I guess my confusion is like when I'm looking at problem 4 with Gandhi, there's nowhere that has that in it, correct?
Right.
There's
one. How many comparisons are? Oh, it's a number. The answer's a number.
Those darn numbers.
Okay. Which one like, it's not in there. So why?
I don't see it anymore.
Also, when you read things.
Reading is good. Which problem was that with Gandhi in it?
Number 4.
Page 107.
Number 4.
My brain is really mushy, y'all. I don't know about y'all, but my kids have been nuts, and I own children, and then all the little cherubs, and I'm just like, I can't.
Well, my day started. I woke up at 4:30. I normally get up at like 5 or 5:30. I woke up at 4:30, and my body's like, it's time to get up. But it really wasn't. But I don't get sleep till about 10 a.m. Then it's too late. So yeah, that's I'm working on that today. Okay, so yeah, you're looking for a pattern that doesn't exist. Okay. And that's the point.
That makes sense.
So it's going to check. So you basically, and I don't like that diagram because it writes the not every time. And that's not really what.
That's what was confusing.
Yeah, what I would have written. In fact, I think in the video that I do write, I would have written an NO the first time. Then I drop down because the NO match, right? Then it's just an N on the next line. And then it's an N. And then it's an N all the way till it finds another N, and then it does the NO, and then you do the NOT. So it uses whether it's capitalized, whether it's checking or not, and I think it's better just not to have it there. But you do.
And on the number 6, am I reading this right? That we are making up our own and then telling the answer for it?
This is number 6 on 107.
String matching. Because that's what I
give an example of a text of M and a pattern of M that constitutes the worst case input for the brute force matrix. Yeah.
So we would give an example of one where it doesn't have it, so it would have worst case.
Yeah, well, like I was saying, if you're looking for Gandhi, if you have the first 5 characters of Gandhi over and over and over and over and over, that's the worst case scenario.
If it does or if it doesn't?
It's going to have the first 5 over and over again. See, it's not just having it not at all, because it's going to zip through. You want to make it think that it's got it all the way till it's at the end. Okay.
So ultimately,
you look confused.
It doesn't.
Yeah. I'm switching to the white pad. So if I don't come back, it's your all's fault. What are we saying? I'm sorry.
It should have it in it, but not find it.
It should almost have
it. It should start it and not find it. Is that what you're saying?
Yes. So let's share the screen here.
Because it has to compare, and then it says, "Oh, I can't," so it goes to the next one.
Yes. So let's say you're looking for kite. I'm not going to make those lines anymore. If we have kit, let's say. Okay. That's really ugly, but you get the idea. As opposed to having all X's, let's say. Okay. All X's, you're just going to check the K, and you're done. Okay. But if you're looking for kite, you're going to do a K. Oh, good. We've got it. Oh, we're still good. Yay. Yay. Oh, no, we're bad. And then you're going to do that K, I, T again, and then the K, I, T again and again, and never get to the E. That's the worst case scenario, right? Does that make sense?
Why wouldn't it go to the next K? Why would it check where the I is if it's already found an I?
Because it's brute force. You're looking forward. There is another technique we're going to use later that's not brute force. Okay. Brute force says you try position 1, you move to position 2. You seem unhappy with that.
I am. Because I feel like if you already compared and found the I, why would it have to go back?
Because it's a stupid program.
Okay.
We're doing brute force. So.
It seems like if you compared something, though, it would know.
It doesn't keep track of that. You're putting intelligence in there. There is a way we're going to do that later, but we're not yet. Not brute force.
So on number 6, it's just a totally made up example that we come up with.
Yes.
That's good because I was reading way too far into that. I'm like, if it's in link, like, and then I have M is going to be, I'm trying to write this whole big thing. I was like, no, I'm waiting until the meeting.
Yep.
That's how I read it the first time too.
Yep. Much easier than I thought it was going to be.
Yep. Okay. What else do you want to talk about? Anything else out of 3.2?
I just want to move to the convex hulls unless anybody has.
I've got a question for 3.3.
Okay.
Yeah.
Yeah, that's convex hull.
Yep.
Okay. Number 2.
I'm just going to say, I've said this before, I think. I love these problems. I love both the convex hull.
Okay, so I guess that means we need to get good at them because we're going to see more of them.
You teachers, students don't get it. Like, I really like this problem. They're like, oh, that's good. You're weird. Yeah, no, that's saying, learn this. You're going to be tested on it. Although you can tell students what's going to be on a test, and I don't think it matters. I often in freshman classes will say, question 1 on the exam is going to be this, and here's the answer. People still miss it. It's like, okay.
Yep. So yeah, number 2, they're just saying, can you design a more efficient algorithm, blah, blah, blah. And I'm like, that's a yes or no question. So we can just say yes and move on.
No.
It doesn't ask us to design anything. It says, can you?
Yes. They should.
That's extremely logical.
Show me. They should. So we understand the problems here, right? The closest point is relatively straightforward. You've got a whole bunch of points and you want to see which 2 are closest together, right? And again, brute force being brute force, we're just going to measure all those pairs. Okay, we're going to do a nested loops so we don't end up doing the same pair twice. Okay, because the distance from point 1 to point 2 is the same as point 2 to point 1. Okay, that feels very n squared, right? When you have nested loops, think n squared. 2 nested loops, n squared. Okay, and that's it. That's all that one does. Okay, the convex hull is a little more complicated to see, but we're just trying to get a set of points around all of the points in your set such that if you pick any 2 points, that subsection is bounded by that, okay, bounded by your convex hull. So that's all we're saying. A hull in general would enclose them all. A convex hull is the smallest such set, okay? And on page 111, I can go ahead and share that. The coolest drawing ever in any math book I've ever seen, I think, is when looking at a convex hull, because this is just so visual that it works out. If you were to take and make an XY coordinate on a piece of wood and you hammer a nail into all the points that you have randomly, if you take a big rubber band, put it around it, snap it shut, the rubber band forms a convex hull, right? Because in this example, every 2 points that you can pick, that line is going to be, that line segment is going to be bounded by the convex hull. So that's what we're talking about with the convex hull. So that's the 2 kinds of problems, okay? So you had a question, what was it, question 2 you were asking about?
Yeah, number 2.
I still don't understand how to
find it.
question 2.
Question 2, the key thing to question 2.
Well, algorithm, so the pseudocode.
Yes. It's worded strangely.
Yes, they all are.
They are sometimes, but this is on a line. So we're only in one dimension. It's on a real line. Okay. So that is the key to being more efficient. So as it stands, the points there are just positions on a line, and they may or may not be in any kind of order. Okay, of how they're going to appear.
So they're lined up.
They're random. They're on a line, but they're random.
Okay.
Point 1 could be 10. Point 2 could be 1,000. Point 3 could be -40.
So we need to put them in order then.
Maybe. That's always a strategy. When in doubt, put stuff in order, see if it helps.
Okay.
But when I first read that, I'm like, what are they even doing? Then I looked at the answer, I'm like, no, I still don't know what they're doing. I'm like, oh, when it says pairs and points, I think 2 dimensions. But no, when it says the real line, we're only talking 1 dimension here.
So like a number line.
A number line. That's the real line, yes. From infinity to infinity.
So if you sorted them, like what Kelly was saying, then the closest pair is the one with the smallest distance, right? Or the difference between the two.
That answer would be too close to the answer, so I'm not going to answer it. I'm going to plead the 5th on that one.
Okay.
Just making sure that like I'm gathering.
Yeah.
So we do need to get an algorithm, like with all the things.
Yes.
There's one on page.
Because I just told how to, but I didn't actually figure it out.
Page, and then she stopped. Are you back, Kim? You said page, and then you froze.
Oh, sorry. 109.
109. Yeah. 109.
Okay, let me go back up to 109.
But that's more complex than what we're doing because it's actual
square root,
not.
Oh.
Yeah, but the form is there, right?
Yeah.
Yeah.
Okay.
So yeah, you can certainly use that. Yeah.
That makes more sense now.
Okay.
So to make that one more efficient.
To make we're still not making the 2-dimensional efficient yet, right? That's a later thing.
That's where I was thinking, and I'm like,
yeah, me too.
We're gonna get there.
Is that what it's saying though?
But,
to make that one?
It's all in a number line.
Okay.
Think number line.
I don't think I get that.
Well, I mean, there's less to deal with. Think about it a bit.
The algorithm on page 109 is for 2-dimensional. So like if you think of a Cartesian plane, putting points on it, and he's saying we're doing it on a number line.
Yes.
So it's not exactly the same, but it's
simple.
Use it as a guide.
Right. I mean, the fewer dimensions, the better. If you have 0 dimensions, you're nothing. Even 1 dimension is pretty easy. But 5 dimensions, it's a whole different set of heartaches. So yeah, it's easier. It's more straightforward. Think about the problem and think about how you would go about solving it. You may, and again, if you just wander around for your answer, that's okay. You're still going to get credit. Okay, unless it's just, and let's say the answer is always 1 million, then that would be crazy. But okay.
So for finding the convex holes on problem 8, like I don't understand what it means by find them. Like, do we need to draw a picture?
No, you can describe it. So let's do 8A. I'll throw you a bone here. You have a line segment. Okay, so let's pop this up. Now, if I don't forget where I'm at. So you've got some point on the real line, some other point. Okay. So this represents this line segment. All the points of this line segment are your set. Okay. So you have to pick the extreme points. Okay. So that for 82 points that are in the set, a line segment between them is in the convex hull. Okay. So you've got one extreme point here, right? You got one extreme point here. The convex hull is the whole line.
Okay.
Because any 2 points that you pick on this line as long as you're covering the endpoints, it's all going to be there. So that's it.
I thought it said in the book that a line segment does not have a convex hull.
No, a line does not have a convex hull, but a line segment does.
Oh, I guess I said it backward then.
Yeah, because a line, there's no way to pick any subset of that. There's no extreme point. Infinity is not an extreme point. Okay, so you can't bound it. Because if you said, okay, my convex hull's from here to here, I can always go beyond that and say, see that segment's not there. Okay.
What's the difference between a square and the boundary of a square?
I meant to take that question out because I really have no idea.
Oh my God, Kim, you like
I actually think I get that one.
Well, it does say in the book that a boundary is not convex. So that's.
Well, I was thinking was a square, they mean like that like basically like planar segment, like that square and all its points inside. The boundary would just be like through the outline.
Oh, okay. That makes some sense.
That's how I took it, as in like you got to find the foremost outer points, the vertices of the square, as long as everything else fits on the inside. Those 4 outside ones are your extreme points, and the convex hull contains everything else.
But then the boundary, this wouldn't work, right? Because that's not in it.
Yeah, I mean, in the book it said that a boundary doesn't have a convex hull.
Okay, so that may not have.
And that would be the reason why, because there are things in the middle.
Yes, that makes sense.
None of that is part of it.
That makes sense. Yeah, I always forget what they mean by boundary. I'm glad that you guys are smarter than me about that. That's good. So yeah, these points are in the square. They're not in the boundary. Makes sense.
So are we doing C or not?
Let's do C, because we now know that yeah, thanks to Tara, we know that the book says that a boundary doesn't have a convex hull, so doesn't have one, which makes sense.
So we're just drawing the diagrams then?
You just have to say, like in this one, what's the convex hull? It's going to be, if it's just the square, it's just the points of the square, right? Those are the extreme points. Because if you include the 4 points of the square, then whatever inside of the square you draw any line segments, it's going to be bounded by the square. So, and again, think of the giant rubber band trick, that if these were all of our points, they're all within the square. If you put a big giant rubber band around it, what's it going to snap to? It'll snap to there, and my mouse got ran over by something. Oh, that's really ugly. You get the idea. that hull is not convex anymore, but you get the idea. My mouse hit something on the desk, but you get the idea. Okay.
Tara, do you know exactly where the boundary is talked about?
I'm thinking it might be on 112. I was trying to look for it, but
let me see. I've got a search on this PDF that I obtained illegally on the net. Yeah, it is.
Oh no, it's on 110.
Yeah.
Yeah. It says any finite set of 2 or more distinct points, the boundary of any convex polygon and a circumference are examples of sets that are not convex.
Yeah. Okay.
What paragraph on 110?
I just saw it and now I've lost it. Oh, it's highlighted in yellow there. It's right under the definition. See right there? I'm showing the screen right. Yes, okay. Okay. Other questions?
I'm ready to go on to 3-4 if everybody else is.
We ready? Okay, move on to 3-4.
Number 3.
3, 4, exhaustive search. Okay, these problems are worth keeping note of in general, and then we're going to see them again. Okay, when we get to the N or N and not N, no, N and NP complete, all that stuff comes up at the end of the class. We'll talk about these. Okay, so we have the traffic salesman problem with the Hamiltonian circuit. We have the knapsack problem. We're going to find ways to get better at this, but there's no really good solution for these. The assignment problem. So make sure you understand what those problems mean. And that's the first part. Okay, which number?
Number 3.
Can I pause really quick before y'all go to that one?
Yes.
Okay, so on the boundary of a square, just real quick, does
Yes.
that mean that it's going to have extreme points or not?
No.
So it's not, okay.
There's no hole.
Okay. Thank you. Now you can move on.
Okay, so number 3. So we're going to algorithm to determine whether a connected graph represented by adjacency matrix has an Eulerian, I'm saying it's Euler, so whatever that turns out with an IN on it, circuit. Okay, so which of those words we understand all those words? We don't understand those words. That's the first question.
I understand all those words.
That's good.
And I'm glad you struggled with the Eulerian as well, because I said it out loud probably 20 times today.
Or Eulerian. There we go.
Eulerian.
I kept saying Eulerian.
Well, I know his name is Euler, so I do.
Yeah. When I first read that sentence, I was so lost because it took me a while to remember what is connected graph, what is adjacency matrix, what is Eulerian circuit.
So this is a more of a generalized version of the bridge of Koenigsberg problem, which I think the book talks about, which is one of the classic things in algorithms. Okay, so it's the idea basically that you have a graph. So we've got the vertices, however they are. They're connected, which means none of them are left out. Everybody connects to at least one thing. Okay, whatever it is. And the question is, so our Eulerian, so I can't say it. Euler's circle, we'll call it a circuit. And I really suck with my mouse, because of the idea. Okay, so for this, it means you have to start at some vertex. You have to travel to all the others and then come back to where you started from. That's what you're looking for. Okay. So the adjacency matrix, with that, it's just so if we have A.
I thought Euler circuits where you had to just cross each edge. Hamiltonians where you've come back, right?
Oh, okay. Really? Is that true? Because Euler's problem, you have to come back. You may be right.
I think you have to end up where you started for the Euler.
That's what I thought too. But then what's the difference between an Euler and a Hamiltonian?
Oh. Where is it?
I'm sure it's somewhere.
Okay, so it says in the book, a Hamiltonian circuit is defined as a cycle that passes through all the vertices of the graph exactly once.
That's the difference.
Okay.
Euler, you can pass it more than once.
Right.
You just have to be able to get back. That's the difference.
Okay.
So yeah, because I know that on the bridge of Koenigsberg,
you have to do the edges. So Hamiltonian is you have to get each vertex, but you could avoid an edge or two depending on how it looked.
Yes.
But the Euler, you have to get every edge.
And you can repeat on Euler, and you can't on Hamiltonian.
Okay. Oh, I didn't think you could repeat. I thought it was like you had to do it exactly once and end up where you started.
You could repeat vertex, but not edge.
Okay.
That may be.
Oh, yes, because you could go like.
Boom, boom, boom. Yeah.
Yeah.
Okay.
Yeah. We should like Google the definition for real rather than making it up.
I thought I understood it right because I looked back in the discrete math book.
Yeah, well, that makes sense. I'm just, I know they're real close, and I know I always have to Google them every time. So let me look them up real quick to make sure.
Yeah, I forgot about you can do a vertex again, but not an edge part of it.
A cycle that travels over each edge in a graph is called a Eulerian or whatever. A cycle that travels over each vertex only once. Oh, it's only once either time. Yeah, so somebody was right. I forget who. The Euler thing, every edge once, the Hamiltonian, every vertex once, and only once. But you still have to go back where you started from. I mean, the cycle part means you come back where you started from. Okay. So hopefully that's more clear. Okay. So yeah, you're looking for something structural about the graph. I think the key there is to start with really simple graphs, like really simple. Okay, like 2 or 3 or 4 point. Okay. And then kind of work up to see what you can tell about those graphs that you would be able to tell on an adjacency matrix.
Well, it says to do an algorithm, so
I mean, yeah, once you find the answer, then you can do the algorithm.
That would have to be for anything, right?
Yeah, I mean, the answer is going to be fairly easily quantifiable once you find the answer.
And the efficiency class, that's going to be, when we're talking about those, they had the 3 different, like the big O and the theta and whatever omega. We're always thinking big O. Is that correct?
Big O is what people use because it's that or better.
It's that table.
Yeah. The big, yeah, the one that's in the middle of the homework or wherever it was oddly located at. Yeah, but the big theta is the most precise because it's exact. The big omega, I don't even understand why you would ever do it, but big O is what people talk about. So if your algorithm can be better, but you don't want it any worse. Okay.
Okay, so make some like examples, work them out, like make their adjacency matrix and see find a pattern.
Yes.
Okay.
That's it. That's how it works. Other questions?
For number 9, I'm not really quite understanding the technique, like how. So like when I first read it, I thought, oh, it's kind of like Sudoku. Like you can't have numbers in the same row or the same
kind of is, yeah,
column. But it also says or the same diagonal.
Yep.
So that I don't think that. But then it says.
Well, that's not part of the problem. That's the classic 8 queens problem. We're not doing that problem. Okay.
Number 9.
Yeah, but it says consider the classic whatever, but that's not what they're asking you to do. They're asking you to do A, B, and C.
Well, right, and that, like, that's what I don't understand. Where it says no 2 queens are on the same square. Well, they're not.
Well, no, but that's the only restriction. Ignore the first part of the problem. They're just saying, in case you've heard of the classic case of placing 8 queens on 8 chessboard, so that no 2 queens, all that stuff. But that's not what we're doing. We've got a blank board. How many ways can you place it so that no 2 queens are on the same square? That's it.
Okay.
Okay. And then the second one, how can you place your queen? How many places can you place the queen so that that no 2 are on the same row? Okay. And then, and again, you're placing 8 of them every time. And then for C, so that no 2 queens are either in the same row or the same column. Okay. So that gets a little more restrictive.
And estimate how long it would take to find them. Well, that could be forever, depending on who we are.
Well, the way you figure those out, you're going to figure out how many positions you have to calculate, right? And you know that this computer is capable of 10 billion calculations per second. So if you get, for example, that B has 10 billion possibilities, it's going to take 1 second, right? If it only has 5 billion possibilities, 5 billion divided by 10 billion is 0.5, so a half a second. So that's all they're doing there. Okay.
Hey, David, on that one, is that like one of the combinatorial?
Yes, it is.
Okay. Okay. So it's like the choose, like how many total and how many you're choosing.
Yep.
Okay.
Yeah, the first one is what? 64, choose 8.
Okay, that's what I thought.
Yep. And as you forgot that, you can just, I mean, in the homework video, which you'll get next week, I not only do it with combinations, you can also just reason it out. I mean, there are other ways to do it besides that. I mean, it's like with, was it the sock problem where there were 45 possibilities? The way I always do those is I have 10 choices the first time and 9 the second. So that's 90 options, which is okay to reason, except you have to realize that a red sock and a blue sock is the same as a blue sock and a red sock. So you divide that by half. You're double counting. So if you don't want to do the combinatorics or the combination of those things, I also, in my answers, do the reasoning out, because either way is okay. If you remember the combinatoric thing, that works pretty well, but you don't have to.
I'm not sure that I remember it, but it makes sense that way. I'm going to have to go back and refresh.
On an exam, if you put C parentheses 64 space 8 parentheses, then you have the correct answer. Okay.
So we don't actually have to work out that math. We just have to understand the concept.
You made it through discrete. You've done that already. You don't have to do it again.
Okay.
So yeah, as long as you can set it up.
I'm sure there's an online calculator that'll do it, or you can always photo
100% is. There's 100% online calculators do this. Yep.
Mathway.
But other questions? The 8 queens problem we'll see again as well. We'll finally get to the full solution, but that's later. Oh no, I began with the yellow card. Does that mean that I have done something? That I have a penalty there, Kelly?
No, it's my bookmark.
Okay. I used to referee soccer, so I see a yellow card. I'm like, oh, that's a warning. At least it wasn't a red card.
It says, read a book or two. Happy Tuesday. By the librarian at my school gave them out to everybody. I was like, I need a bookmark, so that works.
I like it. That's cool. Okay, what else do you want to know?
I'm ready for 3-5 if everybody else is.
Going to 3-5. Yep, we're running out of time, so that's okay.
All right. So number 11.
Number 11.
I know.
I fear number 11.
I know how to do the 3 jugs problem. I know that's like a famous problem. I've done that like a bunch, but I don't know how to apply the search to it. Like that's.
Yeah, this is one you may get, you may not get. So, but think about. So, let's talk about coding this problem. Okay, so a way to transfer into some format what's going on. Okay, so if we say we're going to make a 3-digit number where the first number represents how much is in the, what is it, a 5, no, a 3, a 5, and an 8. Is that right? Yeah.
Yes.
So the first number represents how much is in the 3 pint. The second one represents how much is in the 5 pint. And the third represents how much is in the 8 pint. Okay. So in that coding mechanism, our first guess is 008, right? There's none in the little one, there's none in the middle one, there's only in the big one, okay? So think about, again, this is brute force. What are you going to do? You're going to try to go down every path. So what's one path that you can take? You can pour it into the little one, right? Then you've gone to 105, right? If you pour it into the little one, or the middle one, you would then go a different path, would be 053. Make sense? You look like it does not make sense.
It does. I think I'm just picturing it out and seeing if I'm going to be able to get there.
Don't go too far. Don't get there yet. But yeah, no,
bringing it down to just the 3 digits for each of those jugs.
Yes.
And okay.
Yeah, because you can't really, unless you have a way to deal with these numbers, right?
Yeah. And I think that's what my problem was, is I was like, how does this turn into?
So that's the 3, that's the 5, that's the 8. Okay. So you think from here, what can I do if this were a graph? Okay. So again, I can take this one and pour it into here, which gives me a 3, 0, 5. Okay. Or a different path I could take would be a 0, 5, 3. Okay. And then you just keep working out the options you have at every step until you're out of water. Okay. And see if you can organically come to a solution through this kind of coding. This isn't easy, right? These are kind of like the brain teaser portions of, and again, on the grading, if you don't get this, it's okay. You know, I want to see an effort, but if you don't get it, that's okay. Sometimes you just don't see it.
But
There's still problems I have to look up because I just don't see it. Okay.
I have to get it. That's
I understand.
But no, that really helps. That visual really helped. Thank you.
Yeah, and that one of the big problems we're going to see is how to code things, right? That's the first step. When you're talking about jugs, you can't turn that into math, right? That's physics or something weird. So you turn it into numbers that you can manipulate in an algorithmic fashion. Then you can get your answer. And that really is the key there. Okay.
So are we supposed to show like that diagram or whatever? Or
you have to turn it into what? A depth first, breadth first,
like,
whichever it said. A breadth first search. Yeah. What does that mean? So that's the question.
What I mean, we're supposed to try to solve it.
Yes.
But are we supposed to like show all the option? I mean, like that would take forever. So
no, it's not as bad as you think. It resolves itself quicker than you think.
Okay.
So you kind of map out.
Do we just need to go back and watch the Die Hard movie? I think they do that at the end of one of the.
They may. It's very possible. Yeah.
I just can't get the scene out of my head. I'm trying to figure out what movie it is.
But yeah, there's not an algorithm there. It's just you're solving that in an algorithmic fashion, but you don't have to write the algorithm. So no pseudocode in that one. Okay. And again, if you don't get it, you don't get it. But try to work through it. I want the reasoning more than I care about the correct answer, if that makes sense. I want you to be able to reason. Other questions?
For that problem, I'm assuming like if the 3 pint is full, like if it happens to work out where the 3 pint is full and the rest of the water is in the 8 or whatever, you can pour the whole 3 pint into the 5 pint. It just won't fill it.
Yes.
Okay.
That's correct.
So you can pour, you just have to empty the whole thing into another.
Yes.
Okay.
And what you're looking for here is you're looking for a 4 somewhere to appear, right? When you get a 4, you're done.
Yeah.
So you're trying to do all that you can with these different steps until you get a 4. Then once you get a 4, when you've created this tree of possibilities, going backwards will get you the steps you took to get there. Okay. So that's what that one's all about. Questions? It's easier than summations, right? I'd say yes and no, actually. There's a creative aspect to this. But hopefully it will all make sense. Other questions?
Can you look at 1? Because then 4 says go back to 1, right?
Well, where?
It's on this 3, 5, number 1.
I'll pick number 1. Okay. Yeah. Yes. What about which problem?
I just started writing them in stacks of how it would look. I don't know if that's correct.
Yeah, that makes sense. Yeah, that works. That's a way to do that. Yeah.
Okay.
So you're starting at A, and you're just going to go through the graph, right? Doing breadth first. Breadth first means that you do all the local ones first. So you start off, A is going to go to B, A is going to go to C, A is going to go to D, A is going to go to E, right? That's where you start. Okay.
So you don't like trace a line, like if A goes to B and then B would go to F. I don't know. I don't fully.
That's depth first.
Okay.
Depth first, you keep moving away. Depth first, you go from A to B, and then B to D, and then D to F, and then you got to keep going from there. It's just two different strategies. Do you run away from? So the breadth first, you start from A, and you calculate all of the things on A. Okay. But the depth first, again, would be A to B, B to D, D to F. F has nowhere to go, so you backtrack to D, which has already been visited, to B, back to A. They would do A to C, C to G, G to E, and then it would come back to A, and that would be the whole thing.
Okay, that's what I did, so that's wrong.
That's what I said. You do that for 4? That's wrong for 4. It's correct for
okay.
4.
That's correct for 1. Okay, so I did that for the first one.
Yeah.
I just need to go back and make sure I'm clear on depth and breadth, I guess.
Yes. And again, it's probably worth doing a quick example here of what we're talking about. As far as how I would write those out, I mean, as far as graphically. So again, we've got some random number of points out here that you've got connected in some way. Keep hitting things on my mouse. Just make it unfortunate. Anyway, if we're at 1, 2, 3, 4, 5. Okay, we're starting from 1. Okay, so if we're going to mark them visited by making them red. Okay, so we start at 1. Okay, and we're following, let's say, the breadth first. Okay, so I'm going to go everywhere I can get to from 1. So I'm going to mark 2 as being visited, and I'm going to mark 4 as being visited. Okay, and then from 2, I'm going to go to 3. It's all I can go. From 3, the only one not visited is 5, and then I'm done. Okay, so that's what the breadth first would look like. Okay, where the depth first, I would go from 1 to 2. From 2, I'm going to go to 3. From 3 to 4, and from 4 to 5. Then I'm done. Okay, we're not doing a circuit. We're just doing a traversal. You sometimes have to backtrack. On the one in the book, you have to backtrack back to A to get to the other half of the graph. But that's the idea. Okay. The depth, again, think of depth, you're digging a hole deeper, right? So you're getting further away. Where breadth, you're making your hole wider. So that's what we're looking at.
Thank you.
Okay. Anything else? Okay, we're 8:01, so let's call it a night. And I recorded it this time. Yay. So if you want to refer to this later, you'll have it. Okay, so there'll be new stuff on Saturday or Sunday, and homework's due on Sunday night. Everybody's turning in on time, which is great. If you need more time, if anybody has issues, I know we all got issues, let me know. I don't have a problem with that at all. Okay, and we're on to Divide and Conquer next week, I believe. So it'll be exciting. Okay, talk to you guys later. Have a good rest of your week.
Thank you.